Okay, good morning, everybody. Welcome back to VSPG after the summer break. I hope everybody is doing well and you all had a good summer and your respective field seasons went safely and smoothly, and you got plenty of samples to work with for the coming year. So today we have a presentation by Professor Jesse Reimink from Penn State, how to form a thick Archean lithosphere. And next week, we have a presentation by, by Professor Tony Prave from the University of St. Andrews. It's titled The Grandest of Them All, the Loma Gundi Jatuli Event, and Earth's oxygenation. So you'll want to join for that next week if that sounds good to you. I would like to just show everybody here my since it's been a while and we might have some new people joining, I'd like to just show everybody my screen real quick. Sorry, Jesse.
I'll stop. Yeah, go for it.
And let me get that off of the page. Okay, so this is our website. It's in sort of edit mode since it's on my computer, but our homepage I think is pretty straightforward. For anybody who's interested or hasn't been involved, please, this is where you can get all the relevant information. You'll need to read our code of conduct and abide by everything that we have listed there. One of the unique things about our seminar is that we don't really stop our question session at the end, so that then people can tend to get heated or something, but you need to be respectful. And I reserve all rights to stop anybody from anything at any time, basically. So you can find everything you need here, including how you could nominate a presenter you're interested in hearing from and how to register. We also have a schedule page, our code of conduct page, and all previous seminars, and our speaker bios and recorded seminars. And you can find all those on our YouTube page here. Without it's taking any more time from today's presentation, that's all I have for announcements. So I'll stop sharing my screen, and Jess, you can go ahead and share yours. And I'm going to introduce our speaker today. Dr. Jesse Reimink is an igneous and metamorphic petrologist and isotope geochemist interested in understanding the formation and uplift of ancient continents, focused on the Meso-Neoarchean transition. He is also a pioneer in developing novel, high-precision isotope mass spectrometry techniques, new ways of looking at the zircon trace element and isotope record, and developing geochronological tools for understanding fluid flow and sedimentary basins. Jesse received his bachelor's in geology from Hope College in Michigan and his master's and PhD at the University of Alberta in Canada, where he was studying Precambrian crustal and cratonic development with Tom Chaco. He then went to the Carnegie Institute for his postdoctoral research before his current appointment as assistant professor at Penn State. In addition to his research accolades, he also works together with, I already forgot, Chris Bolhuis. I'm sorry, I probably really ruined that
Close
name.
enough.
Yeah, but they run the Planet Geo podcast for about 2 years now. So little advertisement for Planet Geo. If you're looking for a new outlet for your geology interests or anybody's geology interests, it's a good place to go. So with all of that, thank you, Jesse, for starting us back off, and we're all excited to hear from you. So go ahead and take it away.
Okay, well, thanks, Alex. Thanks for that. overly kind introduction. And thanks for organizing. I mean, you and everybody else who's been organizing this in the last couple of years. I know for me and probably for a bunch of other people, it was a great source of entertainment in some pretty dark days. So thanks for keeping it running, and I'm excited to talk here. So yeah, today I'm going to talk about some work we've been doing, continuing to do in the Archean slave craton up in the Northwest Territories of Canada. I'm going to focus on that, but kind of hopefully try and put it into a little bit more broad context of continental construction in the Archean. And my name, and I'm just the one presenting this, but there are many other people who've been involved. So I'll try and point out the key.
Sorry, Jesse, it looks like I muted you. Sorry about that.
That's all right. Am I back now?
Yes, you are. Yes, you are. Sorry about that.
Okay, no problem. So yeah, we're continuing to do some of this work through some NSF grants, but I'm really interested in the Neoarchean, and I'll sort of try and pitch you as to why that is the case. So I don't really need to do too much of this introduction. I've pulled some slides from some normal departmental seminars where we're sort of trying to get modern hydrologists on board with the early Earth thinking, but we don't need to go through this too much. But okay, we've got this early Earth experienced at least one, probably two magma ocean stages at some point in the first couple 100 million years of Earth's history. And you know, when did we transition to something that looked and operated much more like the modern Earth? In the Archean literature, there's some pretty, I'd say, sound evidence that if there were large volumes of continents in the Archean, they were mostly submerged. This is the pre-3 GA, probably pre-3.2 GA mostly. We have lots of geological and geochemical, I think, evidence for this, some evidence to the contrary as well, but it's an open discussion. And the question for me, the sort of why I'm interested in the Archean is in the Neoarchean is, when did we transition? What drove continental uplift and emergence, and how did that feed back into the solid Earth system? So there's a couple exciting transitions here that both occurred probably during, at least at some point during the Archean. I know that's a very gross generalization, but that's what we're working with today. So to get everybody on the same page, I don't think this group needs to see this, but I always like to show this instead of the IUGS geological time chart, which is, you know, in my opinion, very biased to the Phanerozoic, which I don't really know much about, but you know, we're focused here on the early Earth. So these transitions occurred. This Hadean to Archean transition is very loosely defined boundary, and the Archean to Proterozoic is maybe a little bit better defined, but we're talking about these numbers here, the Hadean to around about 4 GA, and then the Archean to about 2.5. I'm going to focus specifically on this 3 GA to 2.5 transition today, in part because that's what I'm hoping to continue to work on in the next several years here. So we'll be focusing on this Neoarchean interval, and I'm going to loosely define that as 3 to 2.5 GA. So the end of the Archean, which is this time when we went from this Archean water world kind of schematic to something with continental freeboard. Okay. So I'm going to go through a couple Earth system changes, solid Earth system here. I'm sort of pilfering this term from, in part, my department, all the Earth system scientists in my department, and trying to say, oh, the solid Earth is a part of this whole thing. Let's think about the solid Earth system too. So I'm going to go through some changes here. This igneous rock geochemistry, the composition of igneous rocks that are formed at any given time interval dramatically changed in the Neoarchean interval, in this 2.5 to 2.8 really interval. This is a figure from Josh Garber, who's working in our lab, that's in prep, but this has been pointed out in some of the very early Archean TTG or Archean granites literature, and then Keller and Cheney started the whole compilation wave here with big databases. But the point here, this is the sodium to potassium ratio with felsic igneous rocks binned in a moving window kind of a moving window calculation. But the point is that in the Archean, rocks are generally sodic. We've known this for a long time, the tonalite, trondhjemite, granodiorite suite. There's a relatively abrupt change near the end of the Archean, and we start to see what are really potassic granites come on scene and end up dominating for much of the Proterozoic. This is a picture I just took this summer from up in the slave craton. This is a 2.6 billion year old potassic granite. So this is the sort of the arrival of these types of rocks on the scene, which we do not see very much of pre 2.8 or pre 3GA in the Archean gneiss package suite of rocks. So potassic granites arrive. All right, these are true granites. We can see this in map view too. This is a map of the slave craton. So by way of introduction, this is the outline of the slave craton. The colors hopefully are showing up for you. These pinkish or salmon colored rocks are mostly these Neoarchean granites, and they intrude into a metaturbidite package, a Neoarchean metaturbidite package, felsic and mafic volcanic packages, and then those are all laying on top of the basement gneiss assemblage, which is highlighted in green because that's what I'm going to sort of focus on a bit today. So these rocks, once these granitoids formed, nothing else happened to the region for the most part. We have these Proterozoic orogenic belts that are on the margins here, sometimes overprinted small slivers of Archean on the edges. But once those granites formed, not much else happens. The crust was cool and rigid and stable with a deep root. That's the other part of this, is that there's a deep root to this stuff. So this is from recent compilation by Graham Pearson. This is showing the ages. These are mostly osmium, rhenium depletion ages, rhenium osmium ages here of peridotite of xenoliths from the xenolith suite underneath of Archean crust. So what he calls the Archean cratonic mantle. This is the age distribution. When we get to stuff under Proterozoic crust and stuff under what he's calling modified cratonic mantle, and then the lithospheric root underneath of modern oceanic mantle. And the key point here is that we don't have a lot of old ages here. These mantle lithosphere is formed or perhaps preserved for the first time in this 2.3 GA to 2.8 interval. That peak is about 2.65, but there's a fair amount of uncertainty in any one of these ages, so this can spread a little bit. This over here is a curve that shows, this curve is a statistical treatment we did of detrital zircon data sets to kind of say, okay, these are mature sediments, so kind of sort of what we called mature from a detrital zircon perspective. Mature sediments kind of arrive on scene there, and this is a continental growth curve. I can hide something that's blocking my view here. Okay, there we go. This is a continental growth curve, a fairly popular one, although there's some flaws with this. This is the, I think, Dweem 2012 curve here, is suggesting that continents grew and the continental growth rate sort of peaked at around 3G and then leveled off. So the lithosphere is formed or preserved in this interval. We have globally relevant sedimentary packages. This we've known for a long time, going back to Salzman and Hay, where this is the proportion of preserved sedimentary mass in different categories. And we get shales that appear on the scene here in this interval as well. We can recast this in many different ways, and sediments are reworked and are not preserved back in time. But in the Archean, we have a lot more volcanogenic sedimentary sequences than we do sort of true shale basins. So I've tried to compile all of this stuff into a single figure, which I'm happy to take some constructive critiques on here. But this is that I've flipped this. This is potassium to sodium ratio now, and I'm taking I'm binning all the data, that global data set, and plotting a kernel density estimator, so distribution within an age bin. And the point here is that in this cratonization period, this Neoarchean interval, we see this transition from a big peak in sodic. The TTG suite will be in the blue, and the potassic granites will be kind of anything with a potassium sodium ratio above 1 will be in yellow or in orange here. They really start to arrive on the scene in the Neoarchean, the late Neoarchean, 2.6, 2.7. This is a compilation showing the same thing from Oscar Laurent in 2014, where they compiled from a bunch of different cratons. They looked at the transition between TTG and potassic granites. And it occurs at different times in different places, but we have a sort of consistent trend where we get potassic granites and perluminous granites. Chris Spencer and Claire Buchholz have a really nice paper in 2020, I think, 2019 maybe, that looked at the perluminous granites across this Proterozoic to Archean boundary and saw some interesting trends in there, but they are around. Perluminous granites are around up until 2.9, 3GA. And then down here, I've got that cratonic mantle age distribution in yellow. That's just a normalized distribution. So the area under the curve is the total population. And then here I've got it's just a simple number of sedimentary samples from the Stanford SGP database, where I've broken that apart into shales and all sediments, and we start to see a decent number of sediments on the scene. So all things say, okay, we had a decent amount of this stabilization of the crust happened somewhere in this window, or at least the stabilization of decent parts of it happened in this interval. But the question is, what happened before? What happened before the stabilization, before we can look at a rock package and say, oh, this has been sat there since the Neoarchean. All of this stuff predates oxygenation by a few 100 million years. I would defer to the audience to say whether that is coincidence or whether there's some causal effect there. But you know, it's a potential interesting corollary here. So, all right, what's going on in this interval? Just to reiterate, 3GA to 2.5 is kind of what we're focused on here. And I'm going to kind of link this early crustal growth and try and link it to the crustal maturation today. So early formation of crust in the Meso and Eoarchean, Paleo-Eo and Mesoarchean, and then link that to the stabilization in a way. Okay, we don't really know when crust grows. This is a compilation. There's many versions of this, but this is from Jun Kornaga in 2018 in a nice sort of review paper. Bunch of different crustal growth rate curves. There's many opinions about this, and I don't want to wade into that debate, but I do want to say that this is the Hurley and Rand estimation of the current preserved volume of crust, the age distribution of the current continental crust. This is the same kind of curve just with detrital zircon ages. So this is just a cumulative distribution of detrital zircon ages, which we have some growth peaks or perhaps preservation peaks in here where sort of the growth rate increases and then flat plateaus. But this is sort of the minimum distribution. But obviously, we don't know how much Archean crust was out there because we don't have much of it preserved. So how do we know? So we have to turn to isotopic data, which is what I'm going to do in a isotopic data in a geographically oriented space. So to go back to the 50s, when we started to be able to date rocks, this comes from a Carnegie Institution yearbook. I was in what is now the former Department of Terrestrial Magnetism. Unfortunately, this came from the geophysical laboratory side of the Carnegie Institution, which if you know anything about that, we don't really like to quote each other, but the Carnegie Institution yearbook here had some interesting statements about when continents grew. And so they said, oh, it may be possible by modern technical approaches that we could determine whether continents grew by accretion, formation, and erosion of successive mountain structures at the continental margins. And the origin of continents by gradual growth about a nucleus, in the case of North America, is a fascinating hypothesis that may stand or fall on the determination of ages of Precambrian rocks. Well, we know the ages now. And yeah, that sometimes the cores are old. Most of the time, the cores are older than the margins. But what does that actually mean? How much reworking has been going on through time? And this is well represented by some classic work in the strontium isotope database from the Western United States. This is a nice review paper by Jay Chapman, but it's built on a lot of work starting kind of Kistler and Peterman back in the day, where, you know, this is a strontium isotope ratio of modern igneous rocks. These are all younger than about 150 million years, 180 million years. So all these rocks are relatively young. Their strontium isotope ratios reflect the rocks they intruded through, most likely. So the point here is that the isotopic composition of young rocks maps the distribution of old crust. So we can use young rocks to say where old crust is, and I think very importantly, where old crust is not. So on the outside here, the margin, this is juvenile. This is new addition to the continental landmass. This is an old root, and we can trace this with younger rocks. That's what we try and do in isotope geochemistry. Strontium isotopes work this way. I won't focus on that. Many of you know that. We can use hafnium and neodymium in the exact same way. So this is again from this Chapman paper where they compiled, in this case, the whole rock epsilon neodymium, which behaves basically identically to lutetium hafnium. And you can see this trend from juvenile up here, new additions, to seeing older crust. Old crust will be negative in this space. So as we kind of do this transect into the interior, young rocks see the presence or absence of older crust. Okay. Now, on to the slave craton. So this is that map of the slave craton. The value of the slave craton for me, for most of what I've done up until the last couple of years, has been looking at the basement gneiss assemblage. So the green parts here are the basement gneisses. These are older than 2.85 GA basement gneisses, and there are igneous intrusive events every 100, 150 million years from 4GA in Acasta out here on the western margin, all the way to 2.85. There's potentially some age zonation within the basement gneiss assemblage. It's a little bit hard to tell. And then there's a lot of this activity in the Neoarchean here too. Okay, so here's what that map looks like if I take the most recent Northwest Territories Geological Survey compilation database. This is that same exact map. I'll just go back to reorienting. This is Acasta out here, and this is what's called the Cangulic gneiss and the geochemical uplift up here. But the diamond mines that many of you may have heard of are over here, roundabout Lac de Gras area. So this is what that map looks like. The purple are the basement gneisses. The pink and orange are the granites, and we can see these things are kind of intruding in through these are the shale, they're turbidite packages here. And then the green are these mafic metavolcanic belts. And there's some decent evidence that this looks very similar to this sort of dome and keel classic granite greenstone terrain construction, where the granites are doming up through the greenstone belts, which has, sometimes structurally can be interpreted as a sort of vertical tectonic process that could have produced the crust. But the question is, did it produce the crust? Okay, this is what ancient gneiss terrains look like. These are the kind of rocks we're dealing with. These are somewhat well preserved. This is a Paleoproterozoic dike that's been completely disaggregated and boudinaged here. Two different packages of gneiss with a whole bunch of younger intrusive events cross-cutting it. This is another piece right on the Arctic coast. This stuff is toothpaste rock, right? Really kind of difficult to work on. So we have to turn to minerals like zircon that are very valuable. They're very valuable to us because they are resistant to this overprinting that necessarily takes place in a rock. I would not trust the neodymium isotope composition of this whole rock, or at least it would come with a lot of qualifiers in there. But the zircon can record reliable igneous signatures, primary igneous signatures. So good for geochronology. We get ages out of it. We also record the chemical signatures so you can get some process here, and it's preserved through these very high-grade metamorphic events. So zircon's a great mineral. Let's look at the hafnium isotope signatures. I'll just put this on here because many of you know this. Hafnium isotopes, the important point here is that it's all going to be normalized. You take the hafnium isotope ratio, we normalize it into this epsilon notation where 0 is bulk earth or chondrite, the chondrite evolution through time, so they are time normalized. We take the age into account when we calculate this epsilon value, and where positive values will be a depleted mantle signature, or juvenile new crust formation. Negative values in epsilon hafnium will be some interaction with older crust or derivation from older crust. So something enriched led to the granite. So if we form a zircon at this time here, something very negative might indicate felsic crust of that age. Something a little bit less negative might indicate mafic crust of that age, and depleted mantle, something positive might indicate a depleted mantle. Same way as samarium neodymium. Inverse of rubidium strontium. Okay, again, slave craton. Here's some data from Acasta. A bunch of data I've compiled from a bunch of different sources here. This is all zircon data. Most of this is a bunch of zircons from an individual rock to make a single data point. So many of these will have 30 or 40 individual zircon analyses in them that create an average. We get an age and an epsilon hafnium value from this. I've talked about this for a while. I don't want to belabor the point here, but suffice to say there's this negative trend. The oldest rocks in Acasta, 3.75, 4GA rocks, are all negative. They all have negative epsilon hafnium values with this decreasing epsilon hafnium with decreasing age. Negative trend that corresponds well to Hadean mafic crust. If we had a Hadean mafic crust, it needn't be completely theoretical because the Nuvuagatuk samples that O'Neill and Carlson have worked on, although they may not be as old, the composition matches with something like this. So you could be retapping a mafic crustal package to form melts like this. These are new rocks 3.75 that were melting Hadean mafic crust to give us these isotopic signatures. This is backed up by the 142 neodymium system as well. But at 3.6, the important thing is at 3.6, we start to see this spread, and importantly, we have chondritic values at that time. So this led us to propose, okay, there's this shift in Acasta. We went and looked at the global database. So this is a global data set. These are all detrital zircons now. So one zircon and one data point. The uncertainties are a lot larger in both the age and epsilon hafnium for this data. but we have a lot more data to work with. So if we break it apart by region, you start to see, it's hard to see in this plot, we just wanted to show this plot because there's a decent amount of data in here. We start to see this bifurcation in the data set. This is a binned moving average. So we take, or a bin distribution. So we take 50 million year age bins, we make a distribution. The color corresponds to the number of analyses in that age bin. And there's this negative trend, dominantly negative trend throughout the Archean. And then somewhere around 3.8 to 3.6, depending on where you are, we start to see this bimodal signature, which corresponds in most locations to this change from this decreasing trend to something chondritic arriving on scene. And then this remains chondritic throughout the average at least remains chondritic throughout much of Earth history, as has been pointed out by other people. But these values, so that shift corresponds to a shift that occurs in different places at different times, just like in the Neoarchean granite record. Different places have this shift at different times, but it is kind of a consistent signal potentially. So we propose, this is the initiation of a mobile lid crust generation regime in Acasta 3.6, because that's when we start to see the chondritic component come up. But in the Jack Hill zircons, it's about 3.85. In the Wyoming craton, it's about 3.85. Sing Boom is somewhere close to the slave as well. So, this was a proposal. I'm not really super attached to it, but I think it could be useful as a way of thinking about the detrital zircon data. And it has been followed up and maybe confirmed, depending, what you think about that. But by Mulder et al. In 2021, who did a similar analysis with a bit more data. And then Nadia Gerbone et al., who looked at new zircons from the Barberton Greenstone Belt and found a very similar trajectory. Again, this, similar to the Jack Hills, has a 3.8 jump up to chondritic values. So, okay, that's one thing. So we think we might be in a sort of a mobile lid-ish regime. I'm not going to say subduction. I don't really know about that, but we have to have something surface derived that's chondritic, that's melting at depth beneath a proto-continental block. Those are sort of the requirements there. And that's happening at 3.8. So mobile lid tectonics is on the table here. If we look out at the rest of the craton, I looked at the central part of the craton. A majority of my postdoc work was looking at the central part of the craton, which does not contain as old of rocks, but it does contain some decently old ones. 3.4 is a pretty old rock at the end of the day, but these have a very different hafnium isotopic signature. And these are, again, multiple zircons, dozens usually in each of these. This one maybe has 5 or 6. These have dozens of individual zircons that are used to calculate a very robust average for the rock. And they're actually positive. We have positive epsilon hafnium signatures here, which is a depleted mantle-like signature. And you could fit a line that starts about 3.6 or 3.8 through this data. So a depleted mantle could start forming in here. It underwent a depletion event there and would fit this data up until sort of modern depleted mantle lines. Very different from Acasta. Young rocks in Acasta, out here 2.95 GA rocks in Acasta have fairly negative epsilon hafnium signatures. That makes sense, like good, we're happy that works because there's an old rock sitting right next door to it. So it should have a negative epsilon hafnium signature, either by assimilation or by partial melting. Something's happening to incorporate some old parts of that nucleus into this new rock. But in the center of the craton, we don't see any evidence for old stuff. We see juvenile addition, and actually a large volume, much larger aerial extent of these rocks is preserved there. I can put some detrital zircon data from Zircon et al. I'm sorry, I did not put that reference on here. This is a Zircon et al. 2008 geology paper where they looked at detrital zircons that come from these 5 locations, sediments sitting right on top of the basement ice complex. If I separate them geographically like this, then I get this sort of nice divide here as well, where we have most of the old and negative grains are from Acasta or here in the LNF Greenstone Belt. So, this might be an isotopic line or an isotopic division between the old stuff where old rocks are preserved, the young rocks record that. Great, that's as expected. Where young rocks or where no old rocks are preserved, the young rocks do not record old rocks. So there's not a lot of reworking. There's not a lot of massive overprint of the continental crust that is occurring here. These are new juvenile additions to the continent, to the continental nucleus here. So these are detrital zircon samples. The question is, okay, what does this tell us about continental exposure and the eventual stabilization of this continental block? Because I'm sort of invoking a sort of a accretionary type method or accretionary type process here. So epsilon hafnium tracks old rocks geographically. Good, we know that. Depleted mantle appears at 3.3 GA, and it has undergone enough depletion to see it, isotopically see it in epsilon hafnium. And much of the craton is fairly juvenile. Much of the mass of this is juvenile, even in the Mesoarchean. So I could kind of divide this. I can link this with some work from the late 80s and early 90s in the slave craton. This line right here, this black line, is what's called the neodymium or lead line in this part of the world, where if you look at these granites, these 2.6 billion year old granites here, most of these pink rocks are 2.6 billion year old granites. On the east side, they have positive epsilon neodymium values. So came out of the depleted mantle, not much interaction with old crust. On the west side, they have negative epsilon neodymium values and very radiogenic lead isotope composition. So the idea is that granites, Neoarchean granites here on the west, are recording evidence for interaction with old crust. Good, that makes sense. We have old crust exposed on that side, but half of the craton is juvenile. It does not record old crustal interactions here. So this to me is, fairly, well, it's an argument. There's an argument to be made here that this is just simple lateral growth about a pre-existing nucleus that constructed the craton, and therefore then this is the old part of the modern, and it just kind of kept growing and kept getting added to it. So I want to highlight here of a master's student who's finishing up right now, Christy Stoyan, who's found some Acosta-like crust up in this region on the northern part of the slave here. Found a 3.75 billion year old rock up here that we went and resampled that area this past summer. She's finishing up and has done an excellent job and is casting around for PhD projects. And so she'll be at the Geological Society of America meeting in Denver if anybody's going to be there. She's got a poster, so a little advertisement there for her work. But we could potentially even bring the question is, what's this basement gneiss look like? Is Acosta just this little nucleus, or doesn't it extend up in this direction? And then we're thinking maybe it does extend. Okay, so there are, on top of this basement gneiss package, there are cover group sediments. So these are quartzites, conglomerates, and BIFs, banded iron formations that lie right in this interval. They're thin. They're not a huge package of stuff, but Suzette Timmerman, pictured here, who is starting as a professor at Bern very soon, has spent some time during her postdoc working on diamonds that we found in cover group sediments here. So this is the stratigraphy, if I can use that word, of the slave craton. We've got this basement gneiss complex that I've talked about extensively so far. This is the cover group sequence, which is a quartz pebble conglomerate at the base. Some evidence, well, I've never seen a komatiite still, but there's some evidence that there might be some in this package, fuchsitic quartzites, and then banded iron formations. And then we have the sort of younger Neoarchean volcanic eruption, volcanic package. We have some interbedded felsic volcanic rocks, turbidite sequence, and then the granites intrude around 2.6. So all the granite bloom event in the slave is about 2.6 plus or minus 200, plus or minus 20 million years. So we're looking in this sequence sitting right on top of the basement gneisses, and we found some diamonds in this. We found 3 relatively small, these are micro diamonds, but they're detrital diamonds for sure in here. We went back, we went back to sample a sample site that had been sampled in the 90s. It's from up here, had been sampled in the 90s by the Geological Survey of Canada. And they'd found 1 or 2 detrital diamonds, which, diamond research had not been super advanced at that stage. So we could do a lot more with diamonds now. So there wasn't a ton of interest in it. It was curious, but not a lot of focus. So we went up, resampled it, and found 3 micro diamonds from this. And the diamond separation was done in one of the main laboratories that all the diamond companies use. And so it's an accredited diamond separation facility. So we're very confident they came from this sample. And it sits in a quartz pebble conglomerate that looks something like this. In fact, it looks like this. This is the quartz pebble conglomerate. This is Graham Pearson and myself. We were up there this summer, sitting on the outcrop. And this is what this quartz pebble conglomerate looks like. Very Dawson-y. It is a gold target potentially as well. And the exploration company who used to at least have the claim there, like to, for obvious reasons, make analogies to the Wits Basin gold deposits there. But it does have carbon stringers in it, and actually has detrital diamonds in it. The Wits Basin sediments have some detrital diamonds in there as well. But the value of these detrital diamonds is that they are lying in a 2.85 billion year old sediment. So the diamonds we know they're older than 2.85 today. And diamonds form at a very cool geothermal gradient. They form in the roots of continents, the sort of deep roots of continents. So this is the graphite diamond stability field. You have to have a fairly cool geothermal gradient, even just to get diamonds in the cratonic roots. And so we had a thick keel to the slave craton by at least 2.85 or just before 2.85. So diamonds are modern Earth erupted through kimberlites, brought up through kimberlites, deposited on the Earth, and they end up in these quartz pebble conglomerates. And actually, a surprise to me, I didn't know how many diamonds are actually mined in conglomerates. There's a lot of diamond mining that occurs in Proterozoic and modern sediments as well, but we're starting to see a lot of evidence for them occurring in the Archean sediments as well. So it's direct evidence of a lithospheric root. And remember that plot from Graham Pearson's data where the root started, there's really no peak in the lithospheric root in the preserved roots of continents that was older than about 2.9 GA. Not much evidence for that, but we have here some diamonds that are pointing in that direction. So here's a picture of the 3 microdiamonds that we got. We can use nitrogen aggregation, which is a diffusive. The aggregation of nitrogen and diamond is a diffusive process, so it's time and temperature dependent. And if it's sitting in a sediment in the crust, it's not aggregating at all. So this is a really valuable constraint that we can put residence temperatures and times onto. We can use carbon isotopes in diamond to get at the source composition. Where did the carbon come from? And then in this one of these diamonds, this one here, there's an olivine inclusion. So we can use single crystal XRD to get at the entrapment pressure. So this is an example of diamond aggregation at higher temperatures. The percent of these what are called B centers. This is the aggregated state of nitrogen. It aggregates really quickly at high temperatures. At low temperatures, it does not. This is time in millions of years. So over 1 billion years at crustal conditions, it's really not aggregating at all. And these diamonds have very little aggregation. So they did not see a hot mantle for very long. This is a cool signal that we're seeing. The carbon isotopes, apologies for the quality of this figure. This is not very good, but the carbon isotope signatures are heavy. This is heavy carbon. This is a elevated delta C13 value when compared to slave microdiamonds and compared to the mantle field. This in combination with nitrogen gives us a signal that this is surficial carbon nitrogen that was brought down and formed the carbon. That's fairly common in slave craton diamonds. And this is the pressure constraints we get. So again, that single crystal XRD gives us the olivine unit cell parameters, which we can relate to an entrapment pressure. And here's what we get. This green box, and this is a little uncertainty box if we use a different MG number for the olivine inclusion, which we have not measured, but we can make some estimates. And this is the pressure range. So fairly restricted range. We get temperature out of nitrogen aggregation and this pressure out of the single crystal XRD. And this is a paper that Suzette Timmerman just published earlier this year. But this is a really cool geotherm. These are modern slave craton xenoliths. And this is a Mesoarchean slave craton geothermal gradient from, okay, it's 1 diamond, but it's the best estimate we have of a Mesoarchean geothermal gradient through the slave craton and the roots of the slave craton. And so this is quite interesting, we think, and brings up the question of, was this the driver of stabilization of the continental, stabilization record, which I'll end with here in a couple slides. But we can do some modeling. We can look at how could you possibly do this. We can do some thermal modeling of this, which gets a little bit too complicated for the length of this talk, but it's best explained by lithospheric thickening, bilateral accretion. If we do this with a plume, it stays hot too long to have a plume impinge and then stabilize the cratonic root in that way. So we came up with this kind of schematic, which we have this imbrication and diamond formation, this kimberlite eruption. So this lateral imbrication, the diamonds are coming from a superficial carbon nitrogen reservoir, lateral accretion and basin formation, then we get this gold and diamond, and we end up with the modern cratonic lithosphere. And so I think the point here is that from both the crustal perspective, all of the hafnium isotope data that I was talking about, and now the lithospheric perspective, we're forming Mesoarchean lithosphere by horizontal processes, stacking an imbrication of this type of crust. They could be juvenile mafic crust that's forming the TTG suite rocks and bringing in that chondritic hafnium. It's a mobile lid tectonic regime. And to me, this is potentially well, you could make the argument there's progressive growth of preserved continental masses about a pre-existing nucleus. We see this stable continental roots preceded the large turbidite package formation. So it's about 2.6 to maybe 2.72, but more like 2.6 to 2.61, or sorry, 2.66 to 2.61 in the slave craton. And this, so it makes sense that the continental root would help stabilize the crust such that you could preserve and have freeboard. But what it does not help explain is the granite bloom. So this deep lithosphere preceded the granite bloom event by a substantial amount of time. And so the question is, how do you push a bunch of granite magnetism through a thick lithospheric root that is there and it remains in place today, most likely? So that Archean root remains in place today. And I think, you know, trying to punch a plume through that and still preserve this thing is a difficult exercise. And so I think the granite bloom, what this does is it brings up the question of what is causing the granite, large volumes of granitoid magnetism across the craton in the Neoarchean now. And so kind of ordering these things, lithosphere formation, deep lithosphere formation in the Mesoarchean, putting that in order with uplift and the formation of sedimentary deposits and the granite plume event, the granite bloom event, and then ultimately stabilization, which the granite bloom in most cratons represents the final geological event of any real relevance, pan-crustal relevance that happened in these regions. So I think it really brings up some interesting questions about how to link these processes together. What actually drove the stabilization? What was the key process that drove stabilization and uplift of, or at least the generation of freeboard, need not be uplift, but generation of freeboard in this Neoarchean interval. And so we've got some grants to continue working on this. We've up here this past summer, up in this part of the world, sampling these diamond-bearing sediments, looking for old rocks. And then I've got another longer-term award, an SF grant that we're looking at the Neoarchean granite record, because I think it's a really interesting place to test several different models about the Archean Earth. And so with that, here's a subset of the collaborators that I've mentioned, but like I said, loads of people involved in this. I'm just the one who's up here talking about it, so I'm happy to take the questions and abuse, if that's what we're calling it. So thank you very much, and I appreciate your time and questions.
All right, thanks a bunch, Jesse, for that. Really interesting stuff. Like the float plane, I got to sit on one of those this year.
Oh yeah,
so
trip.
If we have questions for Jesse, you can ask in a couple ways. You can go ahead and put it in the chat and I can ask it for you, or you can raise your hand. I see, Roberta, your hand is up, but I'm going to ask a question that was sent to me during the talk first. So you're right up next. But Kaysander Sarwan asks, there's a sharp increase in epsilon hafnium signatures from around 41,000 MA. Is there any reason for this change?
Was this on my plot or from somebody else's data?
I think this was, yeah, I think this was a, well, actually.
I'm trying to think, 4100 MA.
I'm not sure which one. Maybe it's this one. Oh, maybe it's here. Yeah, that's sharp. That's probably what he's talking about. Is the sharp change at 41?
Yeah,
This is the previous slide.
previous slide. Sorry. Oops, wrong way.
Yeah, maybe that's, yeah, there's probably that one.
Yeah, so there's very few data in here. First of all, the colors are these are limited things. So there's not many data from back here. They're probably all from the Jack Hills, and each analysis comes with a decent amount of uncertainty on this. So I wouldn't interpret that as anything, to be honest.
Okay, thanks. Roberta, go ahead, please.
Yeah, thanks, Jesse. That was a really interesting talk. The lithospheric stacking idea for creating cratonic mantle, one of the things I can never figure out about that is that what happened to all of the mafic crust that was originally above the residues? Because a couple of things, those residues are highly depleted. And if you do that by one melting, a single stage melting, then you form something like a komatiite. So you have like a 40% or 30 or 40% melt, which generates a very, very thick sequence of mafic crust or ultramafic crust. And when we look at the stuff that's there today in the lithosphere, based upon xenoliths and based upon diamond inclusions, et cetera, we just don't see evidence for that much eclogite in cratonic lithosphere. So there has to be some way of getting rid of it. And this has been perplexing me for ages.
Yeah, I mean, that's a great question. So you're saying that this sort of package here, when it's sitting off board, is going to have a very thick crustal component, mafic or ultramafic crustal component. And where does that end up? Is that what you're driving at? Like,
yes,
yeah,
that's the question.
Okay. Yeah, okay. So that's a really good question. I mean, I would say my initial reaction would be, well, it's in TTGs, but then the question of where's the residue for that melting, right? And so I think that's kind of what you're getting at, I guess. And I mean, it's a good question. I don't have a great answer to that. A great thought on that. I'd have to think about that a little bit more. I mean, we do see some eclogite in Archean xenolith records, but you're right, it's not proportionally really enough to do the full mass balance. So is there a way to delaminate, preferentially delaminate large blocks of that as it's
right?
Kind of
So there has to be some physical means to separate that crust, which could be much higher density than the residue, surely should be, from the residue, leave the residue behind and get rid of that mafic very high density material. And whether that and so it can't, my point, I guess, is it can't be as simple as obviously your cartoon here.
Sure.
All of that brown stuff is basically gone. I mean, there's a little bit. And how did that happen? And whether it happened, in the, maybe, I don't know, maybe the residue rose, diaperically buoyantly, and the mafic stuff just kept going down. And so maybe there was some form of vertical redistribution going on in addition to,
yeah, that's an interesting point. I mean, I'm trying to think through the density conversions here. I guess, could you get a situation where a slab, if it's not, a modern downgoing slab, if it's a melting slab, let's say it's sort of melting as it's going down there, and we're forming some of the TTGs, could you get a way to have small scale buoyancy, as you're saying, diaperism and delamination going on within the lithosphere?
Yeah, I think
what used to be lithosphere.
Some of Taras Garia's and his colleagues' modeling may have addressed some of that in some of his papers. So, but I guess we just need to think a little bit more. I mean, it's just not very simple.
No, I absolutely agree. Yes, this is a relatively dumb schematic here compared to what it must have certainly looked like. No, I completely agree. That's a really interesting point. I have to think through that. I mean, it also gets complicated when, how do sediments contribute to this sort of process when you start, if this is the tectonics that's going on, which is a big if, what happens when you start to have sediments involved in this? Yeah, it's a great point. I have to think about that a little bit.
Well, you got the fuchsite and the quartzite, which suggests that ultramafic rocks were being eroded, in which case a lot of it would end up as clay, as shale.
That's right. I think Roberta's talking more about the downgoing part or the underthrusting part of this schematic. But yes, you're absolutely right. There is the komatiite that's on this.
The thick oceanic lithosphere would delaminate. And so the crustal part would be tectonically thickened and eroded and weathered. And the depleted lithosphere would be, if I can use the word, subducted or partially subducted.
Yeah, I mean, that's definitely an option. I think we do see, well, we see reflectors in some of the areas as well that look like frozen imbricated slabs, if you want to use that word, or frozen slabs down in there that have not been delaminated. And we see the diamond evidence for at least the carbon and some part of the slab being preserved there still, or I'm using slab. In this model, slab is still, some of it is still there, so it needn't all delaminate. But I think, Roberta, it's a really good point about what's the mass balance of this process. It's a good question.
And a good, yeah, it is a good question.
So we have a couple more to get through here. The Ilya Bindun said, can you comment on geochemical affinity of granites, ocean island basalt, or subduction related?
Geochemical affinity of granites, ocean island basalt, or subduction related. I think I can take that whichever way I want, Ilya. I guess I'd ask for clarification, but I would say that that's a big question. There's people in the room who probably have more insights from a global perspective than I do about the distribution of those. If you want to take the modern tectonic geochemical indicators and map them back into the Archean, I would say it's up for debate and depends on which rocks you're looking at which part of the earth. In the slave cratons, some of these mafic volcanics do have the arc-like signatures. They're the sort of water fluid mobile element enriched signatures. So maybe they're an ocean island basalt that's been accreted, especially in that eastern part of the craton. That was sort of a new addition in the Neoarchean. So yeah, unless there's a clarification, Ilya, I'm not sure.
Yeah, Ilya, if you'd like to try to clarify, feel free, but we'll, I guess we can.
Yeah, I can come back to it too, for sure.
Okay. All right, then let's go ahead. And Jean has a question next. So Jean, you look ready to go.
Would you rather I asked it?
Yeah, I saw you had yourself unmuted, so feel free.
If you could put back the slide of the new Hafnium evolution versus time, going from Hadean to 3 point something, whatever.
Yeah, you said you cut out there. Hafnium. This one.
That'll do. You said that the shift to chondritic values could perhaps mark the start of horizontal tectonics. That might be correct, but I can't follow your reasoning here. If you thicken the crust tectonically, and what you're thickening is that extremely negative Hadean crust, well, the TTGs that come out of it should have that signature and not be chondritic. What that marks must be the arrival of chondritic magmas with chondritic signatures in large quantities. So I don't see how that, you can connect the two there.
Sorry, I think, can you say that again? Because I want to make sure that I understood what you're saying before I accuse you of misunderstanding what I was saying.
You had a cartoon of crustal thickening.
This kind of thing?
Yeah, and you were remelting the imbricated Hadean crust to produce presumably the new TTGs or whatever is giving you that kit, right? Those zircons. Zircons don't crystallize from the basalt, they crystallize from the TTG. So you have to remelt that Hadean crust to generate those TTGs. But that Hadean crust has ubiquitously strongly negative signatures. So
No,
you
yeah.
can't remelt that crust to generate those zircons.
I perhaps was not exactly clear on this explanation, but I think we're in agreement. I agree with what you're saying, and if I misspoke, I'm sorry, because what I meant to say is the early crust, the 3.7 up until about 3.75, we're remelting this Hadean crustal pile, and all the 142 neodymium signatures are negative in these rocks. So 3.75, we're melting the Hadean crustal pile. 3.6, where we see chondritic signatures, we're melting a new juvenile package, a chondritic package is melting, but we have this spread in epsilon hafnium. If I show you the actual data, it's probably a little bit better. Let me move this, sorry. We have this spread in epsilon hafnium. My screen is getting too full here. We have this spread in epsilon hafnium, and this chondritic value, we're melting chondritic crust in bulk, and there is xenocrystic zircon cores in the young rocks. That the young rocks have zircon xenocryst from older rocks. So there's clearly assimilation going on, and assimilation would be the process by, yes, you're in the largest volume of melt is this stuff, but it is being pulled down. It's interacting with that older nucleus. It's not wholesale melting it. You're exactly right. So I would not advocate for pure melting of the Hadean nucleus at 3.6, because it would all be down in here, both in epsilon hafnium and in 142 neodymium. Instead, what we see is a spread from chondritic to the nucleus. So there's a new addition, which is the mobile lid initiation, is what I'm arguing for, which then interacts with the old nucleus by assimilation, is the process we have identified, and so therefore makes the most sense. So sorry if I explained that wrong initially, but
well, it's clear now. You also made the point that there's no evidence for reworking because it's all sort of chondritic, but that doesn't hold. TTGs are not one-stage mantle melts. You have to rework a basalt to generate those TTGs somehow. So there is reworking, but you're reworking juvenile source to generate.
Well, yeah, I mean, it gets. I guess it's I was referring to reworking of prior continental crust in this case, because you're for sure they're second stage melts, but these are from TTGs. And so, the oldest, the maximum depleted mantle model line we can really put through this, unless you want to invoke some magma ocean, crazy composition of depleted something from the magma ocean, the maximum value on a depleted mantle is only about, get my scales right, is only like 4 to 5 at this point. So that intermediate step, the basaltic crustal the lifespan of that oceanic crust cannot be very long. It's got to be at most 100 million years at most, the residence time in that primary crustal package before you start to form these TTGs. So that's the argument I would make specifically about the residence time in the primary or proto-crustal composition before forming the continental crust. But when I was talking about referring to reworking, I was specifically meant to qualify that as continental reworking.
All right, well, it's much clearer now. For the granite bloom story, just read my last 2 papers where I suggest the solution to why they happen. I won't bore everyone by repeating that now, but it's written down. So I'll send you PDFs if you don't have them. Okay,
I'll give it a more thorough read again.
England and Richardson.
Sorry, that came across garbled. I'm not sure.
England and Richardson, crustal thickening plus radiogenic heat and exhumation. And so the granites are made at the top.
I mean, it's
and so you can keep the tectosphere survives.
Mm-hmm. Yeah, I think that's a nice model for it, for sure.
So Ilya did end up with a clarification in the chat. He said arc related is good. So does that help you to address his previous question?
He said arc related is good.
Is good. I think he was just saying you can discuss arc related.
Yeah, it could be. It's one option, one possible option for the mafic packages, and that jives with some of the structural sort of collisional or accretionary tectonics arguments that have been made, especially for the slave craton. So yeah, that's one option for sure. I wouldn't bet on it too much, but yeah, possible for sure.
Okay, and then usually when we run out of questions in hands, we go ahead and just open the floor for people who maybe had something that was a little more specific. Maybe they were holding for a discussion rather than question. So if anybody wants to speak up and discuss something that's been talked, feel free. Okay, and then I treat the silence as a thank you very much. So thank you very much, Jesse, for kicking us off again after the summer. This was really great, well delivered, and looking forward to seeing you around in future meetings as well. So
yeah, thanks for keeping this going. Really appreciate it.
Yeah. Okay, everybody, have a safe week, and we'll see you next time, and when you guys join back in.
Glad to see someone's up there giving blood to the black flies.
Gave a lot of blood to the black flies. They're very happy these days. Yeah. We survived. Actually, the bugs were very nice this year. It was a really dry summer up there. So it was the most amazing summer I've ever had up there doing field work. So grad students got spoiled. All right.
Okay.
Thanks all.
See you guys.